Welcome back to PPT. In this video, I'm going to teach you about equivalence of sets and covering of sets. And then, let's see if we can understand what equivalence of sets and covering of sets. So, let's just dive right in. So, equivalence of sets of FDs. What do you think about equivalence? Why can't we say equal instead of equivalence? Well, equivalence doesn't mean they are exactly equal. In FDs, whenever we are speaking about FDs, if they say F is an equivalent FD to E, you can't say F is equals to E. Okay. This has a separate meaning and this has a separate meaning. This has a separate meaning and this has a separate meaning. Keep that in mind. Always keep that in mind. Okay. So that's why we need to study about equivalence of FDs. All right. So let's start with the definition. Equivalence of FDs definition. Well, two sets of FDs, yeah, two sets of FDs are said to be equivalent, if they have same closure. If they have same closure. If they have same closure. What does this mean? What does this mean? Well, it's very simple. It's very simple. You know what a closure is. Let's say there is a set of FT called F, and we have a set of FT called E. The closure set of F will be called as F plus, and the closure set of E will be called as E plus. If F plus is equals to E plus, you can say F is equivalent to E. You can say F is equivalent to E. So, what can we apply from this? Obviously, we have a definition. We have some rule, some condition that says if F plus is equals to E plus, you can say then F is equivalent to E. What does this mean? Well, you can apply this in a specific context that you can actually derive F from E and E from F. I hope you understood. Okay, I'll write that down. This means you can derive set F from E and vice versa. Why? You can derive E from F2. That's also doable. So let's look at an example. Yeah. Let's look at an example. See, they are saying A functionally determines B and B functionally determines AC, and they're saying C functionally determines A. And there is another set G. Okay, this is F. And they are saying there is another set G that says A functionally determines B, B functionally determines C, and C functionally determines A. Okay. Well, this example is good. Why? I can actually explain you something important. You may have a doubt. Alright. Well, if X functionally determines Y, it's fine. Can there be Y functionally determines X? Is that possible? It's a fair question. Is that possible? Actually, it is possible. If you face something like this, that means that they are mutually dependent on each other. Why? Because from the attributes of x, we can derive y. That's what x functionally determines y means. Similarly, it is also true for the vice versa. Why? How? If y, the contents of y are known, okay, the attributes of y are known, you can use that to find out x. Okay, so this is also possible. Keep that in mind. This is entirely possible. There is no chance that you can say that this is not possible. Okay, if you apply transitivity, it will also doesn't affect the, it will not affect the functional dependencies given here. X will functionally determines x, and y will functionally determine y. So it doesn't matter. Okay, it doesn't matter. But we can have something like this. Okay, we can have something like this. And in this question, I can see that if you consider g, okay, if you consider g, we have a functionally determines b, comma b functionally determines c, comma c functionally determines a. Okay, from these two, okay, from these two, I can come up with a functionally determines c. Yeah, I can come up with that. How am I coming with that? Coming up with that? Well, I'm applying transitivity axiom. Similarly, I can apply here also the transitivity axiom. Not only these two, I can apply to these two too. So I will get b functionally determines a. Okay, I can get b functionally determines a. So you will be thinking like, well, we have a functionally determines b, and we also have b functionally determines a. And in this case, we have b functionally determines c, and I can apply transitivity rule for these two also. Okay, how is that? Well, c functionally determines a and a functionally determines b. So I can come up with c functionally determines b. So we also have that. Okay, and here we have c functionally determines a, and I have already come up with a functionally determines c. So what this means is every single sets of attributes, okay, a, comma b, comma c, all these sets of attributes are mutually dependent on each other. Okay, the information that you are gathering from these three will be similar. Okay, we can say in some cases these three, this is also a possibility when a is equals to b is equals to c. This is also possible when this is true, but we can't actually say that. Okay, we can't actually say that from only functional dependencies. Okay, the attributes, the information they contain, okay, the information that they predict, or the information that they depict, represent, they are same. Okay, they are similar. So if you have to include these, if you had to include these things, okay, if you had to include these sets of attributes into other usages, you can actually use only one and come up with all the functional dependencies instead of using all three, because we know all three is mutually dependent on each other. Yeah, so that's what you have to take away from this example. Okay, shall we continue? So we now have a clear idea on the functional dependencies that you can derive from G. Okay, but in this question, that is not important, because the question asks us to show that F is equivalent to G. For that, I just have to show, okay, for that, I just have to show F plus is equals to G plus. Okay, I just have to show F plus equals to G plus, and that will prove that f is equivalent to g. Okay, so we have f here, and f has a function determines b, b functionally determines ac, and c functionally determines a. Okay, this is what we have. Well, I'll number these things. I have one, and let's say we have two here. Okay, so if I break two, okay, if I decompose two, I will be left with B functionally determines A and B functionally determines C. Okay, that is what I will be left with. So I can say F plus is equals to A functionally determines B, B functionally determines A, B functionally determines C, and what do I have? What do I have? A functionally determines C, and C functionally determines A, and also the second one, which is B functionally determines AC. we already found some of the important ones in G plus, Ilya. In G plus, we found out that A functionally determines B. These are given. B functionally determines C and C functionally determines E. These are given. And we also found out that A functionally determines C and C functionally determines B and B functionally determines A. We also found that. Okay. So what I'm going to do is I'm going to apply union rule here and here, there and there, here and here. And if I apply union rule to these two, I will be left with B functionally determines AC. Illaya? So I can say G plus is equals to, okay, I'll write that down a little bit, I'll write that down a little bit this side, okay, so I can have them all in single line, okay. So G plus is equals to A functionally determines B, B functionally determines C, C functionally determines A functionally determines C. Actually, these are not required, okay? These two are not required because those are not given here, right? Those are not given here, right? But let's just write them down, okay? Because we found that down, so we found that, so we'll just write that. B functionally determines A, and the newcomer, B functionally determines AC. Now I have to show G plus is equals to F plus. Okay, let's cut one by one. D functionally determines AC, found in both cases. D functionally determines A, found in both cases. C functionally determines A, both cases. B functionally determines C, yes. A functionally determines B, yes. Now I have to find out A functionally determines C and C functionally determines B from this one. Well, okay, how can I do that? Well, I have A functionally determines B and B functionally determines C. Look at these two. Okay, from these two, I can come up with B functionally determines A. Okay, so you can say here A functionally determines C from these two, and I can say since I have C functionally determines A and B functionally determines A, not that one. No, C functionally determines A and A functionally determines B, I can say C functionally determines B. Now I can close this and now I can cut these two. Okay, fine. So I have proved that F plus is equals to G plus. This means F is equivalent to G. Okay, so this is the idea behind equivalence of functional dependencies. Covering of sets of FDs. Covering sets of FDs. Covering sets. Okay, so this is also, we have a definition here. Covering of sets of FDs. Here also we have a definition. The set of FDs, F, set to cover set of FDs E if all the FDs in E are also present in F plus. What is F plus? F plus is the closure of F. F plus is closure of F. Let's look at this using notations. Well, we can say if E is a subset of F plus, we can say F covers E. What we can derive from this is E plus is also a subset of, it can be a subset or equals to F plus. This is the possibility. So what is it? If E is a subset of F plus, you can say E plus can also be a subset of F plus. This is what we are learning. Okay, this is what we are learning. Well, how did this come? Well, think of F first of all. Think of F. Well, F in F, you have some sets of FDs. In F, you have some sets of FDs. You have FDs, some sets of FDs. There are some FDs. And when you derive everything that is possible only, if you squeeze the all juice out of it only, you will be coming to the closure F plus. You will be coming to the closure F plus. If if E is a subset of F plus, E must have the entire F plus FDs. Okay, let's say if is equals to, let's deal this with an example, or else this might be confusing. Let's deal this with an example, right? Let's say if is equals to A functionally determines B, comma B functionally determines C. This is the set of FDs. So you know F plus will be equals to A functionally determines B, comma B functionally determines C, comma you can also put A functionally determines C, the transitivity rule. Okay, let's say A is equals to sum of these two. Yeah, sum of let's say these two, B functionally determines C, comma A functionally determines C. We have these two. Okay, we have these two. Well, the thing is, E plus will also be equals to B functionally determines C and A functionally determines C. Why is that? Why is that? Well, you can't derive anything from this. B functionally determines C and A functionally determines C. You can't derive anything. You can't derive anything here. Why? There is no reflexivity, obviously. We can't apply any reflexivity. Are we going to use any augmentation? Well, if you use augmentation, let's say you are augmenting B here. Let's say you're augmenting B here. Then AB will be functionally determining BC. So AB will be functionally determining BE. You can say that, right? According to the reflexivity rule. So AB functionally determines B, and AB functionally determines A. So I can say AB functionally determines C. So that's not a useful thing. So no augmentation is not useful. Okay, augmentation is not useful. So that's not useful. Do we have any other application? Transitivity, obviously there is no transitivity, and we don't have any decomposition. We can have union, but union has nothing to do with this. AB functionally determines C has nothing to do with that anything. And we have pseudo transitivity. Do we have pseudo transitivity? No, no. So we can't derive anything from this. So E plus will also be equals to B functionally determines C and A functionally determines C. Here, E was a subset of F plus. Now E plus is also a subset of F plus. So in this case, F covers E. That's why it's possible. That's why it's possible. Now we'll derive another relationship. Okay, we'll derive another relationship. If F is equivalent to E, we can say F covers E and E covers F, vice versa. What am I talking about? How is it possible? Well, I'll explain it. Okay. If F is equivalent to E, it means that F plus is equals to E plus. That is the meaning, Ilya. If the closure sets of two things are equal, then only two things. By things, I mean sets of FTs are equal, then only they will be equivalent to each other. And we know F plus is equal to E plus here. Okay. And from all these things, we can say F is a subset of F plus. We can say that. Similarly, we can say E is a subset of E plus. I'm going to replace F plus with E plus.
Since F plus is equals to E plus, we can replace F plus with E plus.
Now see, F is a subset of E plus means F plus is a subset of E plus. We can come to that conclusion. And also,
E plus is a subset of F plus.
we can come to that conclusion. How can we come to that conclusion? In this case, F covers E. In this case, E covers F. This is a fun relationship that we can derive. This is a fun relationship that we can derive. What is it? If F is equivalent to E, if F is equivalent to E, you can say F covers E and vice versa. That's all. That's all for equivalence of sets of FTs and covering set of FTs. Okay. In the next video, I will be doing some questions in the basic axioms. Okay, just to test our knowledge. So yeah, let's meet in the next video.
Thank you for joining this exploration of equivalence and covering of sets of functional dependencies. If you enjoyed this video, give it a like and share it with your friends. Subscribe to the channel and hit the notification bell to stay updated with more videos in this series. I'll see you in the next video. Until then, keep learning and stay curious. Bye-bye.